At this point in our study of the bipolar junction transistors, let's just stop and see where we've been before we move forward into our analysis of the small signal, go into the small signal approximations and look at the AC response of the BJT transistors. So thus far, we have seen that the bipolar junction transistor, like the FETs, has three different terminals. One terminal we've referred to as the base, the other is the collector, the other is the emitter. We're going to talk today about, or in this video, we're going to discuss the NPN transistor. So the NPN transistor has the arrow on the emitter going away from the transistor. And we define the currents I sub C, I sub B, and I sub E like that. And we know that this transistor's operation is controlled by and defined by the voltages at the terminals, and in particular the voltages between two terminals, this one being VBE and this one being plus to minus VBC for the voltage from the base to the emitter, the voltage from the base to the collector. As we have seen, there is a PN junction that exists between the base and the emitter and the base and the collector. This PN junction and the current through that PN junction is described by the diode equation we saw when we were studying diodes, or in this case I sub C, the current through the collector, is equal to I sub S e to the VBE over VT, where VBE is just the voltage across this PN junction and V sub T is the thermal voltage. The graph of this equation is the very familiar exponential function, turning on at some point where VBE gets to be large enough that we see appreciable current. And let's point out that we're going to be in this video we're going to be looking at a number of curves. So let's just point out that we need to be looking at what each of the axes represents. So in this graph, the axis here, the horizontal axis, is the voltage across the base to emitter junction, and this axis here is the current I sub C that then flows into the transistor through the collector. And again, we recognize this as the diode equation, the exponential equation, where it starts to deviate, significantly deviate from the horizontal axis when VBE gets to be large enough that it's able to, or that the exponential is big enough to give some appreciable value. And as we saw with diodes, because this is a PN junction, these curves, or this curve, is a function of temperature. And the greater the temperature, T1 being the greatest of these, the earlier the diode begins to conduct, or the diode conducts for lower values of VBE, the greater the temperature. We've seen that we can think of the operation of these diodes in three different regions, or the transistors operate within one of three different regions or modes of operation. The mode of operation being determined by the relative terminal voltages. So again, we've got the collector, the base, and the emitter, and the relative voltages at these terminals determine which of the modes the transistor is operating in. When VBE is less than some value, in the book that we're using it says nominally less than about a half a volt, this PN junction is reverse biased, and no current is flowing through the transistor. This region is referred to as the cutoff region. Both PN junctions are reverse biased. As VBE gets above 0.5 volts, the diodes, or this PN junction starts to becomes forward biased, and at some point, nominally 0.7 of a volt, we say that the transistor is moved into its active region. So the base to emitter voltage at around 0.7 of a volt causes this, or provides a forward bias on this PN junction, and if there's still a reverse bias on this, or in the active region, there will still be a reverse bias on this PN junction. So the transistor is in the active region when the PN junction here between the base and the emitter is forward biased. yet the base to collector PN junction is still reverse biased. And in fact, we say that we'll be in this mode of operation as long as VBC, the voltage from here to here, is less than about 4/10 of a volt. As that voltage increases, either by the voltage of the collector dropping or the voltage of the base increasing to the point that this junction is greater than about 4/10 of a volt, at that point the transistor then moves from the active region into the saturation region, and we'll talk about that in just a second. But in the active region, the three currents, the collector, the base, and the emitter currents, are all of the form of e to the VBE over VT. But they just have different scaling values. I sub C is equal to I sub S e to the VBE over VT. I sub B is equal to 1 over beta times that, or I sub C is equal to beta times I sub B, where beta is a parameter, it's a quantity that is a function of or determined by the physical characteristics of the transistor itself. Different transistors will have different beta terms. But I sub C then is equal to beta times I sub B, because if we just sum the currents coming in here, we have that I sub E is equal to I sub B plus I sub C. We've shown then that I sub E is equal to beta plus 1 times I sub B. So the point is that all three of these currents are exponential in form, and they have different scaling factors, and the scaling factors are related to each other. Finally, as we mentioned, when this base to collector PN junction becomes forward biased at around 5/10 of a volt, something in there, we then run into the saturation region where electrons in the N-type collector are free. There's no voltage barrier to prevent them from flowing into the lightly doped, narrow base, lightly doped, p-doped base region. And we have then electrons flowing in and completely overflowing or completely saturating the base. Any holes that existed in the base have now recombined with electrons, so that in the saturation region the base is completely depleted. There are no unbound holes there. And we then stop thinking of the transistor as being two separate PN junctions. We just think of it as being a continual semiconductor, a continual piece of silicon with a surplus of electrons. At that point, the collector or the transistor is said to be saturated, and there is the voltage from the collector to the emitter, VCE, becomes relatively constant at what is known as the saturation voltage, or VCE sat. That saturation voltage runs between anything below about 3/10 of a volt. 3/10 of the volt would be perhaps on the border between the active and the saturation region. 2/10 of a volt across the collector to the emitter would drive it far into the saturation region. At that point, the voltage, or the current between the currents of the collector and the current of the base are still can be thought of as being a scaled version of each other, or better yet, the ratio of the collector current to the base current then, I sub C over I sub B, is much less than in the active region, and we can define that ratio as being what we're going to refer to as the forced beta. And the forced beta, or the ratio of the collector current to the base current in saturation, is significantly less than the ratio of the collector to the base currents in the active region. So that describes then the relationships between currents and voltages within the transistor itself. And we have seen that we can place a transistor into a circuit. We can connect to these terminals voltage sources and resistors that influence the terminal voltages. And by doing so, we say that we bias the transistor into the active region where there is a relatively linear relationship between voltages at the input and the output. Placing the transistor into this circuit then introduces some external dynamics on the voltage and current relationships, and as we've seen, we then have a second expression for I sub c. I sub c is equal to VCC minus VCE divided by R sub c, or VCC minus VCE divided by R sub c. Now if we rearrange, well, before we do that, thus we have two equations for I sub c, but you'll notice that they are of a different nature. This expression here is the exponential relationship between I sub c and VBE, which we derived for the transistor itself, and this I sub c is a function of the surrounding circuit. Because they are of different form, we can't just simply set them equal to each other and solve for either VBE or VCE. It's tied up in the exponential here. It's out here. If you're to, typically the way you would solve this is you would take the logarithm of this side, and then you'd get at VBE. But then these variables here would be tied up in the logarithm. So they're different in nature, and this type of situation doesn't lend itself to an analytical solution. So if we take this equation and rearrange it, we come and solve for VCE. We then have VCE is equal to VCC minus the voltage drop across this resistor, or VCE is equal to VCC minus I sub c times R sub c. If we then place in for I sub c the exponential relationship, we then found this expression here. This expression then led us to what we call the voltage transfer curve, or the VTC. This provides us a very useful relationship between the output voltage, VCE, as a function of the input voltage, VBE. And this equation holds for the cutoff region on through the active mode, or the active region of the transistor. And as we see for as we have seen for small VBEs, this component here is relatively small and stays small until we get up to a point where the base to emitter junction starts to conduct, and then we start seeing this part in here until VBE gets so large that the voltage across the base to collector forward biases. The PN junction here becomes forward biased, and the transistor enters the saturation region. So we've now seen that this active mode, there's a relatively linear, although it is exponential, don't get us wrong, this curve here is an exponential curve. There's a good portion of it that is relatively linear. And it's at that point, or within this region, that we then can have a linear relationship between the output, or between this input voltage VBE and the output voltage VCE. And as we've seen, very small changes in VBE correspond to very large changes in VCE, and that's how we get amplification out of a transistor. And again, the purpose of these external resistors are to bias the transistor, to place it within the circuit at some quiescent point, some bias point, that allows room for variations in the output without either running into the cutoff mode or running into the saturation mode. So in this circuit we have these two different equations describing the equations, describing the relationship between the voltages and currents. And as we've pointed out, there is no analytical solution for it. So another graph to look at, another interesting graph, graphs the output voltage VCE and the current IC. So what we're doing is we're looking at these graphs become a graph of this current as a function of VCE. And as we pointed out, there are actually three different quantities that are associated with this. You've got I sub c, VBE, and VCE. Thus we end up with a family of curves. Each one of these different traces corresponds to a different value of VBE, and we then have I sub c as a function of VCE. The second equation is a linear equation in terms of VCE. And so superimposed on this I sub c graph is what is known as the load line. The load line is the graph of this equation where, as you can see, the slope of the graph, this is of the form, this is the y-intercept b plus mx. So the x variable, the horizontal variable, is VCE. The slope of this line is 1 over r sub c, and of course it's negative. And then the intercept here is v sub c, or VCC over r sub c. So VCC over r sub c. And the horizontal intercept is where VCE equals VCC. And the bias point then corresponds to the point where the load line intersects the trace, and that intersection then gives us the value of VCE. So for this bias point, it corresponds to a specific I sub c value, a specific VBE value, and a specific VCE value. Those three quantities then constitute the bias of the transistor. And as we can see, because the slope of this line is 1 over RC, different values of RC then establish different load lines with different slopes. And our purpose, the purpose of biasing them, is to place the bias point, or to the resting point of the transistor, to allow for the type of amplification you're wanting. This load line here corresponds to an R sub c that may, depending upon what you're wanting to do, well, first of all, it establishes the bias point here. And as you can see, VCE corresponding to that is a value of VCE that is relatively close to the source, the power supply voltage VCC. So in this case, there's not a lot of room for variations around, for the output to vary very much in the positive direction before you run into the power supply. We say that there's not a lot of headroom with this type of a bias, but there would be a lot of foot room. Another example here is another load line that corresponds to a different R sub c. In this case here, VCE may be too small for regular amplification because we're really not very far from transitioning into the saturation region. In other words, VCE, the voltage from the collector to the emitter, is relatively small and is approaching that 0.3 value where the transistor then moves from the linear active region into the saturation region. So we have four different graphs, or three different graphs. We've got this graph here showing the I sub c as a function of VCE. We have the voltage transfer curve, which shows the output voltage VCE as a function of VBE. And then we have the diode equation, or the graph that shows the I sub c current, the current flowing effectively through the transistor, as a function of VBE. And that's one of the places where this gets to be confusing, why transistors confuse people sometimes, is we don't take enough time to sit down and analyze these graphs and look at just what it is that it's showing. Each of them is useful. Each of them is useful for different purposes. So let's wrap this up then. In the transistor amplifier circuits, we bias the transistor with DC voltages and resistors to place it into this quiescent, or this resting place where the transistor is on. We then superimpose on that a smaller signal that we want to amplify. And by staying in that linear region, by not letting these variations in VBE get too large, we stay within that linear region, and we can then think of and do our analysis of these circuits in terms of this large DC signal circuit involving only the DC values, or the bias circuit, plus some small signal. The total output then corresponds to the bias conditions plus the small signal. We can remove the bias conditions with the capacitors and then talk about just the small signal operation of the circuit. So that's where we're at now. We're pretty well done with the DC biasing calculations. We're ready now to move into the small signal approximations and look at the small signal models for the BJT transistor.